Just want to welcome everyone to the first lecture with Robotics and Introduction. So this is going to be a very basic introduction. I'm going to set some grounds for terminology, so a few concepts, and then digging a little deeper before we go into things like electronics. And I want to start with what are electronics, circuits, resistors, all that kind of fun. But before doing that, explain, well, what are robots? What is robotics? Why are we looking into electronics at all? What are some basic components and building some terminology that we will use in this course and give you a starting foundation. So as always, I shall shrink myself down. Boop, boop, boop. And we will begin. So I like to do things in threes, and sometimes having someone else give a voice that to what are robots can be good. And this is why I want to bring in these videos, to kind of give you a first basic context, maybe some additional information, and then I'll go over other concepts that tie to what you'll see in these videos. And they have also a way bigger budget and more time to do editing than I ever will.
Hi, I'm Carrie-Anne and welcome to Crash Course Computer Science. Today we're going to talk about robots. The first image that jumps into your mind is probably a humanoid robot, like we usually see in shows or movies. Sometimes they're our friends and colleagues, but more often they're sinister, apathetic and battle-hardened. We also tend to think of robots as a technology of the future, but the reality is they're already here by the millions, and they're our workmates, helping us to do things harder, better, faster and stronger. There are many definitions for robots, but in general, these are machines capable of carrying out a series of actions automatically, guided by computer control. How they look isn't part of the equation. Robots can be industrial arms that spray paint cars, drones that fly, snake-like medical robots that assist surgeons, as well as humanoid robotic assistants. Although the term robot is sometimes applied to interactive virtual characters, it's more appropriate to call these bots, or even better, agents. That's because the term robot carries a physical connotation. A machine that lives in and acts on the real world. The word robot was first used in a 1920 Czech play to denote artificial humanoid characters. The word was derived from robota, the Slavic language word for a forced labourer, indicating peasants in compulsory service in feudal 19th century Europe. The play didn't go too much into technological details, but even a century later, it's still a common portrayal. Mass-produced, efficient, tireless creatures that look humanesque, but are emotionless, indifferent to self-preservation, and lack creativity. The more general idea of self-operating machines goes back even further than the 1920s. Many ancient inventors created mechanical devices that performed functions automatically, like keeping the time and striking bells on the hour. There are plenty of examples of automated animal and humanoid figures that would perform dances, sing songs, strike drums and do other physical actions. These non-electrical and certainly non-electronic machines were called automatons. For instance, an early automaton created in 1739 by the Frenchman Jacques de Vaucanson was the canard digérateur, or digesting duck, a machine in the shape of a duck that appeared to eat grain and then defecate. In 1739, Voltaire wrote, "Without the voice of Le Maire and Vaucanson's duck, you would have nothing to remind you of the glory of France." One of the most infamous examples was the Mechanical Turk, a chess-playing humanoid automaton. After construction in 1770, it toured all over Europe, wowing audiences with its surprisingly good chess playing. It appeared to be a mechanical artificial intelligence. Unfortunately, it was a hoax. There was a dainty human stuffed inside the machine. The first machines controlled by computers emerged in the late 1940s. These computer numerical control, or CNC machines, could run programs that instructed a machine to perform a series of operations. This level of control also enabled the creation of new manufactured goods, like milling a complex propeller design out of a block of aluminium, something that was difficult to do using standard machine tools, and with tolerances too small to be done by hand. CNC machines were a huge boon to industry, not just due to increased capability and precision, but also in terms of reducing labour costs by automating human jobs, a topic we'll revisit in a later episode. The first commercial deployment was a programmable industrial industrial robot called the Unimate, sold to General Motors in 1960 to lift hot pieces of metal from a die casting machine and stack them. This was the start of the robotics industry. Soon, robots were stacking pallets, welding parts, painting cars, and much more. For simple motions, like a robotic gripper that moves back and forth on a track, a robot can be instructed to move to a particular position, and it will keep moving in that direction until the desired position is reached, at which point it will stop. This behaviour can be achieved through a simple control loop. First, sense the robot position. Are we there yet? Nope, so keep moving. Now sense position again. Are we there yet? No, so keep moving. Are we there yet? Yes, so we can stop moving and also please be quiet. Because we're trying to minimise the distance between the sense position and the desired position, this control loop is more specifically a negative feedback loop. A negative feedback control loop has three key pieces. There's a sensor that measures things in the real world like water pressure, motor position, air temperature, or whatever you're trying to control. From this measurement, we calculate how far we are from where we want to be, the error. The error is then interpreted by a controller, which decides how to instruct the system to minimise that error. Then, the system acts on the world through pumps, motors, heating elements, and other physical actuators. In tightly controlled environments, simple control loops like this work okay, but in many real-world applications, things are a tad more complicated. Imagine that our gripper is really heavy, and even when the control loop says to stop, momentum causes the gripper to overshoot the desired position. That would cause the control loop to take over again, this time backing the gripper up. A badly tuned control loop might overshoot and overshoot and overshoot, and maybe even wobble forever. To make matters worse, in real-world settings there are typically external and variable forces acting on a robot, like friction, wind, and items of different weight. To handle this gracefully, more sophisticated control logic is needed. A widely used control loop feedback mechanism is a proportional integral derivative controller. That's a bit of a mouthful, so people call them PID controllers. These used to be mechanical devices, but now it's all done in software. Let's imagine a robot that delivers coffee. Its goal is to travel between customers at 2 meters per second, which has been determined to be the ideal speed that's both safe and expedient. Of course, the environment doesn't always cooperate. Sometimes there's wind and sometimes there's uphills and downhills and all sorts of things that affect the speed of the robot. So it's going to have to increase and decrease power to its motors to maintain the desired speed. Using the robot's speed sensor, we can keep track of its actual speed and plot that alongside its desired speed. PID controllers calculate 3 values from this data. First is the proportional value, which is the difference between the desired value and the actual value at the most recent instant in time, or the present. This is what our simpler control loop used before. The bigger the gap between actual and desired, the harder you'll push towards your target. In other words, it's proportional control. Next, the integral value is computed, which is the sum of error over a window of time, like the last few seconds. This look-back helps compensate for steady-state errors resulting from things like motoring up a long hill. If the value is large, it means proportional control is not enough, and we have to push harder still. Finally, there's the derivative value, which is the rate of change between the desired and actual values. This helps account for possible future error, and is sometimes called anticipatory control. For example, if you're screaming in towards your goal too fast, you'll need to ease up a little to prevent overshoot. These 3 values are summed together with different relative weights to produce a controller output that's passed to the system. PID controllers are everywhere, from cruise control in your car to drones that automatically adjust their rotor speeds to maintain level flight, as well as more exotic robots like this one that balances on a ball to move around. Advanced robots often require many control loops running in parallel, working together, managing everything from robot balance to limb position. As we've discussed, control loops are responsible for getting robot attributes like location to desired values. So you may be wondering where these values come from. This is the responsibility of higher level robot software, which plans and executes robot actions like plotting a path around sensed obstacles or breaking down physical tasks like picking up a ball into simple sequential motions. Using these techniques, robots have racked up some impressive achievements. They've been to the deepest depths of the Earth's oceans and roved around on Mars for over a decade. But interestingly, lots of problems that are trivial for many humans have turned out to be devilishly difficult for robots, like walking on 2 legs, opening a door, picking up objects without crushing them, putting on a t-shirt or petting a dog. These are tasks you may be able to do without thinking, but a supercomputer-powered robot fails out spectacularly. These sorts of tasks are all active areas of robotics research. Artificial intelligence techniques, which we talked about a few episodes ago, are perhaps the most promising avenue to overcome these challenges. For example, Google has been running an experiment with a series of robotic arms that spend their days moving miscellaneous objects from one box to another, learning from trial and error. After thousands of hours of practice, the robots had cut their error rate in half. Of course, unlike humans, robots can run 24 hours a day and practice with many arms at the same time. So it may just be a matter of time until they become adept at grasping things, but for the time being, toddlers can outgrasp them. One of the biggest and most visible robotic breakthroughs in recent years has been self-driving autonomous cars. If you think about it, cars don't have too many system inputs. You can speed up or slow down, and you can steer left or right. The tough part is sensing lanes, reading signs, and anticipating and navigating traffic, pedestrians, bicyclists, and a whole host of obstacles. In addition to being studied with proximity sensors, these robotic vehicles heavily rely on computer vision algorithms, which we discussed in episode 35. We're also seeing the emergence of very primitive androids, robots that look and act like humans. Arguably, we're not close on either of those goals, as they tend to look pretty weird and act even weirder. At least we'll always have Westworld. But anyway, these remain a tantalising goal for roboticists that combine many computer science topics we've touched on over the last few episodes, like artificial intelligence, computer vision, and natural language processing. As for why humans are so fascinated by creating artificial embodiments of ourselves, you'll have to go to Crash Course Philosophy for that. And for the foreseeable future, realistic androids will continue to be the stuff of science fiction. Militaries also have a great interest in robots. They're not only replaceable, but can surpass humans in attributes like strength, endurance, attention, and accuracy. Bomb disposal robots and reconnaissance drones are fairly common today, but fully autonomous armed-to-the-teeth robots are slowly appearing, like the Samsung SGR A1 sentry gun deployed by South Korea. Robots with the intelligence and capability to take human lives are called lethal autonomous weapons, and they're widely considered a complex and thorny issue. Without doubt, these systems could save soldiers' lives by taking them off the battlefield and out of harm's way. It might even discourage war altogether, though it's worth noting that people said the same thing about dynamite and nuclear weapons. On the flip side, we might be creating ruthlessly efficient killing machines that don't apply human judgment or compassion to complex situations, and the fog of war is about as complex and murky as they come. These robots would be taking orders and executing them as efficiently as they can, and sometimes human orders turn out to be really bad. This debate is going to continue for a long time, and pundits on both sides will grow louder as robotic technology improves. It's also an old debate. The danger was obvious to science fiction writer Isaac Asimov, who introduced a fictional 3 laws of robotics in his 1942 short story Runaround. And then he later added a zeroth rule. In short, it's a code of conduct or moral compass for robots, guiding them to do no harm, especially to humans. It's pretty inadequate for practical application, and it leaves plenty of room for equivocation. But still, Asimov's laws inspired a ton of science fiction and academic discussion, and today there are whole conferences on robot ethics. Importantly, Asimov crafted his fictional rules as a way to push back on robot as a menace memes, common in fiction from his childhood. These were stories where robots went off the rails, harming or even destroying their creators in the process. Asimov, on the other hand, envisioned robots as useful, reliable, and even lovable machines. And it's this duality I want to leave you thinking about today. Like many of the technologies we've discussed throughout this series, there are benevolent and malicious uses. Our job is to carefully reflect on computing's potential and peril, and wield our inventive talents to improve the state of the world. And robots are one of the most potent reminders of this responsibility. I'll see you next week. Crash Course Computer Science is produced.
The Crash Course series I find very useful for a lot of things. Now, in that one you get a feel for some of the ideas of this external sensing stuff from the environment, taking that input, reacting. If certain conditions are met, then certain reactions come out of that, and that continuous cycle and that kind of loop. You also see things where it's branching from the physical to the software to the artificial intelligence, and again, robotics and artificial intelligence is one area. AI is a much bigger field than just robotics. And you also get things like ethics that you have to worry about, interactions, HCI kind of stuff. It's a wider range than you think of just the basics. Okay. So now, this is another robotics video. This is a newer one that they did, but it gives another overview that helps add more to the conversation that we'll have coming up.
Someday in the near future, you might be wandering around town at night when out of the blue, you'll stumble across a robot. If that happens, maybe you shouldn't be too surprised. Not so long ago, robots were mostly found in the realms of science fiction. Today, they're vacuuming floors, building cars, and even roaming around the surface of Mars. Robots are still pretty far from having a human-level capacity of intelligence, or even dexterity for that matter, but they're already a big part of many branches of engineering. In the US, over 100,000 robots have been added to factory floors since 2010. Knowing exactly what robots are, what they can do, and how they work is more important than you might think, because soon they might be living among us. The classic picture of a robot is something with human-like intelligence and maybe even a humanoid appearance. But like so much else, real-life robots aren't much like what you usually see on TV. Robots come in all shapes and sizes, and they can be built very differently depending on what they're used for. For example, some of the robots used in mining are made from a camera mounted on a small chassis with wheels. That allows them to enter and inspect mine shafts and even retrieve leftover material from places it's hard to get people in and out of. Meanwhile, in medicine, specialized robotic arms, with a bit of human assistance, can perform precise surgeries through the tiniest incisions. There's also a difference between robotics and artificial intelligence, or AI, which people sometimes confuse. While some of the concepts are similar, robotics deals with a specific set of ideas, although it does borrow a few from AI. AI deals broadly with the goal of automating decision-making for complex tasks, the kind you can't write a simple set of rules for. That could be everything from playing chess to driving cars. Right now, AI systems tend to have very narrow goals, but the holy grail of AI is to develop a system that can make intelligent decisions about any sort of task using different sources of information. Our focus will be on robots which are designed for more specific purposes in the physical world. In engineering terms, a robot is a machine designed to interact with its environment, make an appropriate decision based on those surroundings, and then carry out the jobs related to its goal, all automatically. Which means a true robot doesn't require a human controlling exactly what it does. In general, the field of robotics also deals with machines that do all of the same things, but might require a human operator to carry out some tasks. Whether fully automatic or not, virtually all robots have a few features in common. First, robots are machines made from materials that occupy physical space, so they're more than just lines of computer code. That's one of the key features that distinguishes them from AI, although computer engineering is important for robots as well. Second, most robots have some way of sensing features of their environment, usually by measuring light, sound, or force feedback. They can then use that information to make a decision about what to do next, depending on what they're designed for. The tasks robots are built for tend to be complex, requiring a sequence of different motions. So an automatic door that opens or shuts in response to whether you stand in front of a sensor wouldn't be considered a robot. The tasks that robots handle are more sophisticated, like welding two intricately shaped pieces of metal together. Third, to interpret the signals they receive from their environment and coordinate some sort of response, robots have computers built somewhere into their design. These work just like any computer, taking inputs and delivering outputs. But unlike most ordinary software, the software on a robot's computer generates electrical signals that are directly passed onto the robot's hardware, instead of just changing information in a file or on a screen. That also requires a power source. One option is to physically hook up to the power grid using wires and a socket. For example, the 2013 version of the Atlas robot, developed by robotics company Boston Dynamics, had a humanoid design that could walk and carry objects much like humans do. To operate, Atlas relied on a cable that tethered it to a power supply. But tethering robots like this limits how far they can move and interferes with the robot's mobility. So to let Atlas move around more freely, engineers installed a battery on the robot's structure so it could power itself. Unfortunately, the materials of a battery tend to be rather heavy, which posed its own challenges. If we don't want robots like these toppling over all the time, it takes a bit of mechanical engineering know-how to work out where to position the battery with respect to the robot's centre of mass. You might need some chemical engineering in the design of the battery too. In the case of Atlas, engineers gave it a hydraulic pump in its torso to help it support the extra weight of its lithium-ion battery. And now, only a few years later, it can do backflips and parkour. More generally, some electrical engineering also has to go into wiring the signals from the computer program to the robot's physical parts. Which brings us to another common feature of robots. They have mechanical parts like grips or wheels for carrying out whatever physical task they need to in their environments. That might be turning a lever, picking up an object, or just moving somewhere else. And there are some unique challenges to designing those parts. Consider a robot designed to pick fruit from trees. From an engineering perspective, it needs some fundamental qualities. The ability to recognize fruits and distinguish them from the rest of the plant, navigate its environment to move toward the fruits that need picking, and then to pick them and put them into a container. Let's start with how it moves, a fairly basic requirement for lots of robots. Like with the mining robot, you could simply put some standard axles with wheels on the bottom of your robot and attach them to a motor, like on a car. That would be fine if the robot was going to be operating mostly on smooth, even surfaces like roads or factory floors. But most fruits are grown outdoors, sometimes in rough terrain and difficult environments. So you might need to design adjustable wheels that change height independently or add treads to overcome small bumps like on a tank. The problem with wheels is that they're not very good at overcoming large obstacles. If there's a fallen branch or a boulder blocking the way, the robot needs to be able to climb over it. Giving the robot legs could allow it to jump, but that has its own problems. Robots with legs tend to fall down. A lot. As the team at Boston Dynamics found when designing Atlas, programming a robot's computer to interpret its environment while handling the dynamics of all those mechanical parts is trickier than it seems. It really makes you appreciate what a good job your brain is doing. Of course, to actually make sense of its environment and find fruit, the robot will need sensors. Devices that measure physical characteristics and translate them into a signal. To find apples, for example, the robot might have an array of light-sensitive semiconductors, like the kind that make up light-capturing pixels in a digital camera to scan an orchard. But the information sent by the camera sensor is interpreted by the computer as an array of coloured pixels that don't mean an awful lot on their own. The average person can take one glance at a curvy shape of reddish pixels and instantly recognise it as an apple. For a computer, that requires a fairly sophisticated visual algorithm. What's more, people are good at seeing where the edges of objects are and interpreting the relationship they have to their environment and how far away they are. You know, an apple that looks very small is most likely one that's very far away. But even a relatively smart computer that can recognise apples might not know whether it's a tiny apple only a few centimetres away or an enormous apple a few kilometres away, which would affect whether the computer's programming tells it to pick the apple or not. All of these issues are what are known as computer vision problems. Computer vision deals with how to train software to take the input data from images or video, like the kind that are delivered from digital cameras, and interpret it the way a human would. Even once it's found an apple and moved itself close to it, the fruit picker is going to need mechanical parts to actually pick the fruit. The main mechanical parts used by most industrial robots are called actuators and effectors. Actuators are like robots' muscles. They convert stored energy into movement. One popular type are electrical actuators, electrical motors that turn wheels or gears to rotate the robot's connected parts with respect to one another. These are the sorts of mechanisms that would extend the robot's arm toward or away from a particular branch. Linear actuators can achieve this by using a motor to extend the part up and down a thread, like a nut on a bolt. They can also use compressed fluids like air or oil to extend a part outwards, then use a motor to compress the fluid and bring the parts back when needed. Effectors, meanwhile, are the parts that actually have an effect on the robot's environment, basically the robot's hands. To deal with the irregular shapes of different fruits, you could have what's called a vacuum grip that can suck up large objects and hold them in place. But most of the focus on building robots has been on mechanical effectors, the kind that rely on tactile feedback and manipulating. In other words, they give the robot an artificial sense of touch, perhaps with force-sensitive electrodes on the effector's surface. Having a sense of feedback is important for applying the right amount of pressure, otherwise the apple might slip out of the robot's grip or be crushed into a pulp. To achieve this, the effector might be a simple two-part claw or something more sophisticated with many parts modelled on a human hand. Picking fruit is the kind of job that robots could accomplish at scale, much more easily than humans, freeing them to work on other aspects of farming. But robotics isn't just aimed at saving labour. Robots can also be used in environments that are far too dangerous to send humans into. Bomb disposal robots, which are actually more like drones, are operated by humans to find explosive devices and disarm them from a safe distance. In the future, fully automated robots might find uses in other harsh environments, like the deep sea and space. But it's likely that the place robots will have the most impact won't be in the jobs they do instead of humans, but the ones they do alongside them. Features of robotics are already making their way into healthcare. like in the development of prosthetic limbs. But in situations like surgery or disaster rescue operations, a combination of human smarts and purpose-built robotic strength could create safer, more efficient, and totally new ways of doing things. So like many engineering tools, robots will work best when they weave into our existing methods, working alongside us to accomplish our goals. Robots might be the future, but it's a far cry from the Terminator. In this episode, we looked at robots and the engineering principles of robots. We learned how robots use sensors to interpret their environment, how actuators and effectors allow a robot to manipulate the objects around it to accomplish a task, and how computers coordinate the efforts of the two.
So, now these are two videos. That's good, like 20 minutes in here, but this gives us a wide feel for like, well, what is the field of robotics? And there's a lot of areas you could go into, and we can't in the 4 months that we have here, but I still want you to give you a feel of everything that goes on. And as we go deeper into the physical body environment and interaction of robotics and these kind of mechanical devices, and then work with things like Arduinos, which are types of controllers. So, introduction to robotics. So, going back to, again, this in the videos and giving our introduction, that a lot of times those first views, if you're telling people, like, what is a robot, you're going to think of, like, the creatures we see here on the left. Is something that seems humanoid, that's been given some kind of shape that we can interact with or identify objects and kind of humanize them. But you remember, that's not the only thing that's out there. That they don't just look like that. Like, not all humans are this robot, android-esque, and have limbs and things that we're used to. There's a lot more things, and all the devices and everything that we use and see around us every day. So a robot is a machine that executes a series of actions automatically, is one of them. Is like, okay, well, given an action, a button press, and the series of actions will happen. Or some kind of stimuli from the actual environment, and it goes through its actions. Or, say, more complex thinking, environment, and planning goes on, like with the self-driving cars. So robots are, in fact, defined as man-made mechanisms, devices that can possibly move themselves, whose motion must be modeled, planned, sensed, like actuated, controlled, and whose motion behavior can be influenced by programming. So you've got like these physics environment of actual equipment, body, and things that come in as chemistry, everything else you got to take into account. You've got the software, digital side of this. And if you're doing any tasks, it's got to be coordinated, it's got to be planned, it's got to be gathering information continuously while the task is happening. It's not as simple as just running a loop and saying, hey, go over there. It's got to be a continuous level of, well, what sensors do we have? How fast are we reading and reacting? And if we don't react fast enough, we could have something that slams into a wall before it even realizes that there's a wall there at all, because the speed at which it's processing or accessing the information that's coming in. You have this blend of this like concrete digital world, but with the chaoticness of real life, and trying to balance of how do we deal with those two things together. Now, I still brought in some of the history stuff. From here, I think it's just good to know where this comes from, and the fact that a lot of times the terms and stuff we're dealing with have been influenced by science fiction literature and the arts, and there's not such separation between the arts and sciences and computer science. Just because there's different classes doesn't mean that they're not combined together. So even that term robot, that first view of it, a robot, a forced labor, drudgery, that's the kind of thing that we use it as a device that does this work continuously for us and works together. And then if you start to go beyond that to AI and the idea of the singularity and like sentience, what could that mean for the future, being these separate automatons? Robotics itself is a study and application of robot technology. And this is a wide area, so from the engineering to computer science to, like, again, artificial intelligence, chemical engineering, mechanical engineering. Like, a lot of things have to come together to, like, build that robot in the end. And it's a wide area of study that branches out further than just this course. And tying back to, again, science fiction from it here, is the term robotics was first used or coined in short stories in 1942 by Isaac Asimov. And some of us, or all of us, may know about the three classic laws of Robotics from Asimov that a lot of his stories center around. So, an interdisciplinary field that integrates computer science and engineering. Robots involves design, construction, operation, and the use of actual robots. And even nowadays, it's starting going into more of the ethics from this. If you're dealing with sentient, you're dealing with self-driving cars and ethical decisions having to be made, well, you also have to deal with that philosophy and other kind of worldly action of like, well, when you're designing this, what effects could this actually have? It's not just making a robot. Maybe, yes, we're designing something that's a lethal automaton, but is that what we want to do, and what other issues come out of it? Is it something that will provide a better for the world, or is it, I'm just doing my job? It's a whole study and field on its own that people can go into, and I'm also interested in letting people in this course, if they want to do projects, kind of branch out into that kind of ethical realm. And not by ethical realm, I mean making things that like shoot and fire and attack people. That's a no from right here. I mean the ethics, like that study of what is ethics and AI and machines that have to make decisions. So, like, robotics integrates fields of like mechanical engineering, electrical engineering, information engineering and design, mechanics, electronics, bioengineering, computer science, artificial intelligence, control engineering, software engineering, amongst other, like, many things. It's a lot of fields that are coming together and a lot of areas that you could go about studying this. And even breaking it down, if we look here, even though I'm using like the humanoid robot, is, well, different parts of it break down into other fields and cross over. And this is just a general kind of diagram that you see here. Is you have things like, well, if it's the brain or any kind of components throughout, even things that control things that are within the arms and legs that are then all communicating together as different subcomponents that come together. You have areas of fields like computer science and artificial intelligence, machine learning, and system hardware, and kind of control coding that. If it's sensing stuff, so getting that input from the external or inside the body or construction itself of the actual robot, you've got electronics, embedded systems, control theory, like electrical parts, like the physics, the core of the body itself, like physics, mathematics, like everything else. So what do you expect? Where do you place stuff? What is the weight? It's not just having the sensor, but what do you do with the body itself? And like mechanics, materials, designing, what is it made of? How will it react? How does it do everything? And bringing all of these together. And like, I can't go into all of these in one course and make something that's coherent that wouldn't just be this tiny little bits throughout. But this is supposed to be the beginning course that you could go further and realize how many things have to come together to make that robot, let alone other areas that you could branch out and actually study. Even, say, if some of you are taking the HCI course, Human-Computer Interaction, there's a whole area you can deal with robotics within there. Like, if we deal with these physical and communications, you have a crossover with, like, interaction and guidance kind of stuff with the external environment. Like, how does it work and deal with that? If this is a humanoid, how do you interact with it? Like the UI UX experience of working with that kind of machine or robot. How does it visualize information? Speech, if it's something that's supposed to talk, going back and forth, and gestures and everything else. And that's a whole different design. That may not be the electronics, but just the rest of the actual design and what you can do. Now, for this course, I said, like, I don't really want to spend 4 months just going over little bits of each actual topic. I'd like to dig down into one, get a starting point where you're dealing with something kind of hands-on, and then allow you, if you want to go past this course or even for the project itself, is kind of go deeper into one of those areas that you may be interested in or expand beyond it. So for this course, we're going to be concentrating more on the electronics and embedded systems, a little bit of the control kind of stuff, not very like theoretical math-wise, but more the hands-on of like, well, okay, if we're working with physical materials, if we're hooking stuff together, how do I hook stuff together and then do some coding to interact with and read information from that sensor, then send stuff out to those actuators or effectors and get some kind of interaction, get some loop that's checking for conditions to be met before it triggers to go on to do something else. Now, digging deeper from here is we've got to think about, at least I want to think about it this way in this course, of the robot being the mind, body, and its environment. Being like, well, the physical parts and components, constructions and placement and body of the actual robot itself, the environment it's interacting within, and then the actual software mind thinking controls coming all together. Because it's not like we can just write a piece of code, but that's just going to be a program, and that's no different than anything else. But having that program then controlling and reading things from physical actual devices, and then all of it being put into some construction body that you want to do to interact with that environment at all. And you have to take it all into account. And we'll start with just some electronics, just getting it to read data, but then you'd want to start thinking about, well, where would I place the sensor? What effect does that have? Once it's operating, and if it's moving at all, movement can cause things to break down. What happens when things break down? And then what happens, like, can you detect that breakdown? What can you do with that? And taking that all into account. And the fact that, like, other environments, like the drawing here of like the Mars rover, of like that physical body and that's long distance away, how is it getting its information? What does it do? How does it interact? And I'll have all of this has to come together. And we'll step our way up from there. But still, the fact that you have that internal digital software, you have the internals of the body and externals, and you have that interaction then with the environment, and that sensing and that kind of loop continuously happening. Now, one of the earlier videos talked about a control loop, again, more terms, and for this course, I just want to use the term, the robotic control loop. Now, if you go into other fields, there's going to be a lot of different terminology, maybe with your own experience, and so for here right now, I just want to use this as one common term and terminology, and a way to visualize things in this course. So, if we're once again looking at robots of the external environment, the sensors, these physical devices that are translating stuff from that physical environment into digital signals, which then programs can read and then interpret and then send out actions to other components that can then translate that electronics and energy into physical movement or change or some kind of action or lights or whatever. You have this continuous idea of this loop of always, well, sensing what's happening in the environment, thinking about it and reacting. The fact of like taking in the inputs, spending the time to think about what's going on from here, taking out actions, and maybe changing over time based upon certain conditions that have happened, like move, move, move. Oh, we're at the drop point. Okay, drop now. Okay, move, move, move. And like keep doing this. And you're always going through this loop. And you're going to see this a lot when we're dealing with stuff with adrenals, is that this constant of it's always whirling. And the effects that you can have forever is that if you're sensing forever and never going to thinking, well, nothing's going to happen. If your thinking takes too long, well, then you're not applying action. So what's happening while the software is running versus the actual robot in a physical environment and that kind of sensing? So say if it's a robotic vehicle and it's moving forwards and you have this program that's running really slow and it's not taking any more sensor input and it's not doing any actions, and if it's too long in between that point in time, it may crash into something because it hasn't read some sensors to update and think. So you have to worry about, well, how fast is the device, the controllers that we have, how fast can the programs and how efficient can they actually run, how long am I spending on a task in the computer fast processing terms of like doing some execution of some actions or thinking before moving on to the actual next step. So get used to seeing this sense, think, act loop of like take input from the external environment, react and think to and check conditions, and then make changes based upon that, and then go back to sense and continuously going within this actual loop. Because if we start with things like sense, this is bringing in information from the external, which could be completely different. Like if we're designing something for this course, we're going to always have to have something that's external, because otherwise there's no new point. If it's just a program that's making a screen, that's nothing that's different, or having a light or moving something. You got to have some kind of sense of interacting of what's going on in the environment. And these are other devices that we will use and get into in the course and talk and get a little bit deeper with them. But you think, well, like, which ones can I have? What needs to be connected up for them? Is there physical limitations that I can't just instantiate a new variable and make as many as I want? If there's sensors, like maybe it's only have this one sensor and I can't have a lot of them. And there's issues with having it. So the physical limitations and where you place it and taking that into account. You know, do we have something to do speech or vision or temperature? Is that even possible? Is there limitations on the quality? because you can have really expensive sensors, which we don't have access to in this course, to really cheap $2 to $3 ones, which will get some input, but just won't be as good. So how do you react when you know that's not as good input, but you still want to do something with it, and vice versa? And whatever you want. So you want to think, well, what sensors are out there? What are devices? And these are physical electronic devices that then hook up to another controller, which will have your program and are located physically somewhere in that actual body. The thinking part of this. So we'll start with a lot of very simple stuff, and we're not going to go really into the AI side of that. That takes more complex controllers, other work. If you do work with Raspberry Pis, and we'll get into like Raspberry Pis and Adrenos and what are the differences and all the other type of controllers as a starting point for the course. Well, what could you do with it? But that thinking is that task planning, classifying the inputs, learning maybe as you're going, processing the data, finding a path if it's moving, motion, and all the rest of the stuff. It depends what you're doing, the task you're working on. It's going to be more complex to less, but this is more the digital side, and it's going to be taking that input sensors and then based upon preconditions, if it's matched, then sending stuff out to the actual actions and actors to do stuff and make changes to the actual environment. And that final part being acting, again, based upon the thinking phase, the environment, it's going to make changes like outputting information if you have a little screen or something, or lights in some way, moving, speech, text, moving something like a servo or motor, so forth. Like, it all depends upon that. And so we get this continuous, again, cycle of sense, think, act. Take the external environment, digitize it, think about, execute some actions based upon that, and then convert that digital into some kind of other motion to give some kind of feedback to that actual environment. Because just like having no sense, having no act, then what's the point? You're not seeing something come back from the actual robot. You have to have some way of indicating what it's actually doing. Some of the examples of work in the very beginning are just going to be a lot more sense, act, and the think part's going to be very simple to start with, but that can grow based upon the task you're actually trying to work on. So I want to keep digging deeper. We're working our way down to electronics and basic electronics we start with and building our way up. We want to dig deeper. We know we have that sense, think, act, but we need to have some more terminology and dig deeper into the physical body of the actual robot yet. Like when we talk about sensors, well, what really is that? What other terminology do we have in these components when we think of it that are doing these sense, think, act? And it'll dig deeper even further from here. So this is just one layer of that kind of onion, and we're going further and further. So for this course, I want you to think about most things that we're working with could potentially have a combination of a lot of these things. Like, you're going to always have power, you're always going to have controller, and you're always going to have some kind of sensors, but depending on what your effectors and actuators are. So we have these 5 things of having sensors to read information in, effectors that are going to actually change the environment around us. You have actuators, which are effectors, but they're more, I just want to use the terminology in this course to represent that's meant the stuff that's moving or changing the actual environment, whereas effectors could be lights and other stuff. So think of effectors as the bigger and the actuators as the subcategory. And I'll be going through all these in a second. You have controllers being a physical device, but that's where the thinking and execution actually happens. Then overall, the actual power source is that we need food, we need energy to do stuff. The robot is going to need some form of power, and these all have effects on everything. So digging a little deeper into sensors is that without any sensors, our robots could be considered to be deaf or blind to the environment. They can't take stuff in. And so you could have multiple of the same, and where you place them, what is in the body, what type you actually have, but you need to have that. Like this fictitious little humanoid robot that we have here, having vision sensors, sound sensors from right here as this overall part of it, but they provide a limited feedback to the robot so that it can do its job and gain feedback about what is happening in the actual environment itself. Now, the sensor sends information in the form of electronic signals. So this is, we'll get into that, electronics, we know, electricity and signals that are actually being sent from the sensor to the actual controller itself, where the thinking kind of brain part of it is. And these signals can either be analog or digital. And don't worry, we'll talk about these when we get into electronics. So what does that mean between analog, which is more waves, versus digital, which is up, down, just kind of zeros in a basic sense. And we'll learn more of that. And the fact that these different sensors, some are analog sensors, some are digital sensors. And what does that mean how do we use them, and how does that hook up to the actual controller, say part of it. But this is all part of that kind of sense part of taking stuff in from the actual environment. And we need those electronic devices that convert external information like light levels, sound levels, distance, motion, and stuff like that into information that then can be processed in a program that you're used to. Say, like if you're writing a program and you're reading something from the user, well, we're reading stuff from the environment and having to then interact with it in the program that we're writing. Now getting to the think part, this is all your controllers. So this is whatever your component is that's taking these inputs in some way, processing it, has a program generally loaded on or other multiple programs, and can be different levels of complexity from very simple to very complex, larger devices. Basically like computers, but we have to get back to microcomputers, microcontrollers, and what that definition is. But this is a whole family of it, being the controller overall, and we're only going to work with one type of control in the course, but I want you to know that you can investigate others. They're coming in. So it's the brain of the robot, the hardware that contributes to processing sensor information and triggering action. So like CPUs, something like that, microchips. It involves the mechanical aspect of the actual programming, so bringing it in. And a lot of times these controllers have specialized things that you wouldn't see in your general purpose computer, that they provide ways to hook up these actual sensors in different ways, and the actual like effectors and actuators that do stuff externally. Now the actuators here, as I said, this is a subcategory of effectors. And so like actuators is an effector is any device that affects the actual environment. I just screwed up the names and slides. So like actuators and effectors between it. You can see in between, like if we go more to like the diagram itself, like saying these grippers or these motors, is that actuators, that what makes them different is that they're going to deal with actually moving the robot itself. So that anything that's the motion, if it has to move, if it has moving components that will move the robot from point A to point B, I like to refer to those as actuators. And these are being motors and stuff that are included here. Whereas effectors themselves are just going to make some kind of changes externally. Like if it's sound, could be an effector. Light from lights could be an effector, because they're going to change some output, like what you're seeing in the actual environment itself, or do some kind of motion or move or something combined overall. And like actuators, as I said, so again, effectors, anything that changes the external environment of the actual robot. So lights, sound, motion, and actuators are more specifically defined as the things that'll move specifically. And I just want to use the terminology so when we talk about these overall. And lastly, power is you don't give the robot power, nothing's going to happen. And you have to worry about that again, like this in the videos, of where do you place that? Is this a power source like batteries or something else that's going to be on the device? Is it plugged in directly to power from the computer? How much power, being like levels, and how does that affect it? The more things you hook up, and everything you hook up consumes more energy. So just like you doing more physical work and carrying more weight, and you're going to need more food and energy to do your work, well, for a robot, the more things you hook up and the more complex or larger they are, it's going to require more power, and so power has an effect. And if it's battery sources, well, batteries run out. So what starts happening when that doesn't work? You know, like when you haven't eaten anything all day and you're getting sluggish and you don't think right, well, the same thing will happen because the controller needs power to run. And if there's less power or it's getting weaker, it's going to start run weird, and weird things will start happening. Things that you're not actually used to. Okay. So we're almost at the end of these slides here, and this is just more of a quick introduction. And I know for this lecture it's only like about an hour, but I wanted to give you that first overview and idea into like what's everything that's going on with robotics, and get some terminology to start with, and realize, why am I going to electronics? Why is it important to understand that? Because, you know, if all these components are built of electronics and we're hooking together, well, you need to understand, well, what is the basics of electricity? What's the basics of electronics? And if the physical body in these components are there, well, if I'm hooking things together, what does that entail to do? And then how do I hook that to a controller? Then how do I write programs that read information? And that's what we're going to start doing. We'll start just dealing with some basic electronics and hooking it together and getting an idea of circuits, electricity, resistors, and kind of components. and then start moving on to, well, okay, well, how do I tie that into controllers, and then how do I connect that together, and then how do I start writing programs that read information in different ways and do that, then how do I start stepping then back up to more complex robots that we work with. So what I want to end off with is just a video here from Crash Course again, but about robots and AI. And this is meant more as extra information for some context, because we're not going to really go into the AI into this course. That's too much to go into. That's its own field as well. If people are interested for the projects, they can start doing some kind of research around it and see, well, what would that take to actually do? But we'll start with a basic kind of AI and then see, well, there's way more complex things that could actually go on. And so I thought this would be a good video just to give you some context of robotics and AI. The AI specifically for robotics. AI is a wider area than just robotics itself.
Hi, I'm John Greenbot, and welcome to Crash Course AI. Today we're learning about me.
Hey, this is my show.
Uh-oh.
It's okay, John Greenbot. We can do the intro together. Robotics is a broad topic because it's the science of building a computer that moves and interacts with the world, or even beyond the world, in space.
So today we're going to talk about robots like me and what makes us tick.
Some of the most exciting AIs are robots that can move through the world with us, gathering data and taking actions. Robots can have wings to fly, fins to swim, wheels to drive, or legs to walk. And they can explore environments that humans can't even survive in. But unlike humans, who can do many different things, robots are built to perform specific tasks with different requirements for hardware and for learning. Curiosity is a pretty amazing robot who spent 7 years exploring Mars for us. But it wouldn't be able to build cars like industrial robots or clean your apartment like a Roomba. Robotics is such a huge topic that it's also a part of computer science, engineering, and other fields. In fact, this is the third Crash Course video we've made about robots. In the field of AI, robotics is full of huge challenges. In some cases, what's easy for computers, like doing millions of computations per second, is hard for humans. But with robotics, what's easy for humans, like making sense of a bunch of diverse data in complex environments, is really hard for computers. Like, for example, in the reinforcement learning episode, we talked about walking and how hard it would be to precisely describe all the joints and small movements involved in a single step. But if we were going to build robots to explore the stars or give me a snack, we have to figure out all those details, from how to build an arm to how to use it to grab things. So we're going to focus on 3 core problems in robotics: localization, planning, and manipulation. The most basic feature of a robot is that it interacts with the world. To do that, it needs to know where it is, which is localization, and how to get somewhere else, which is planning. So localization and planning go hand in hand. We humans do localization and planning all the time. Let's say you go to a new mall and you want to find some shoes. What do? You start to build a map of the mall in your head by looking around at the walls, escalators, shops, and doors. As you move around, you can update your mental map and keep track of how you got there. That's localization. And once you have a mental map and know the way to the shoe store, you can get there more quickly next time. So maybe you plan that the escalator is faster than the elevator. The most common way we input that data is with our eyes through perception. Our eyes give us 2 slightly different views of the world, which allow us to see how far away objects are in space. This is called stereoscopic vision. And this mental map is the key to what many robots do too if they need to move around the world. As they explore, they need to simultaneously track their position and update their mental map of what they see. This process is called simultaneous localization and mapping, which goes by the cool nickname SLAM. But instead of eyes, robots use all kinds of different cameras. Many robots use RGB cameras for perception, which gather color images of the world. Some robots, like John Greenbot, use 2 cameras to achieve stereoscopic vision, like us. But robots can also have sensors that help them see the world in ways that humans can't. One example is infrared depth cameras. These cameras measure distances by shooting out infrared light, which is invisible to our eyes, and then seeing how long it takes to bounce back. Infrared depth cameras are how some video game motion sensors work, like how the Microsoft Kinect could figure out where a player is and how they're gesturing. This is also part of how many self-driving cars work, using a technology called LiDAR, which emits over 100,000 laser pulses a second and measures when they bounce back. This generates a map of the world that marks out flat surfaces and the rough placement of 3D objects, like street lamps, a mailbox, or a tree on the side of the road. Once robots know how close or far away things are, they can build maps of what they think the world looks like and navigate around objects more safely. With each observation and by keeping track of its own path, a robot can update its mental map. But just keep in mind, most environments change and no sensor is perfect. So, a lot goes into localization, but after the robot learns about the world, it can plan paths to navigate through it. Planning is when an AI strings together a sequence of events to achieve some goal, and this is where robotics can tie into symbolic AI from the last episode. For example, let's say John Greenbot had been trained to learn a map of this office, and I wanted him to grab me a snack from the kitchen. He has localization covered, and now it's time to plan. To plan, we need to define actions, or things that John Greenbot can do. Actions require preconditions, or how objects currently exist in the world, and actions have effects on those objects to change how they exist. So, if John Greenbot's mental map has a door between his current location and the kitchen, he might want to use an open door action to go through it. This action requires a precondition of the door being closed, and the effect is that the door will be open so that John Greenbot can go through it. John Greenbot's AI would need to consider different possible sequences of actions, including their preconditions and effects, to reason through all the routes to the kitchen in this building and choose which one to take. Searching through all these possibilities can be really challenging, and there are lots of different approaches we can use to help AIs plan, but that would deserve a video on its own. Anyway, during planning, we run into the third core problem of robotics: manipulation. What can John Greenbot's mechanical parts actually do? Can he reach out his arms and interact with objects in the world? Many humans can become great at manipulating things. And I'm talking about objects, not that force power stuff. Like, for example, I can do this, but it took me a while to get good at it. I mean, just look at babies. They're really clumsy by comparison. Two traits that help us with manipulation and can help our robots are proprioception and closed-loop control. Proprioception is how we know where our body is and how it's moving, even if we can't see our limbs. Let's try an experiment. I'm going to close my eyes, stretch my arms out wide, and point with both hands. Now, I'm going to try and touch both index fingers without looking. Almost perfect. And I wasn't way off because of proprioception. Our nervous system and muscles help our body's sense of proprioception. But most robots have motors and need sensors to figure out if their machine parts are moving and how quickly. The second piece of the puzzle is closed-loop control, or control with feedback. The loop we're talking about involves the sensors that perceive what's going on, and whatever mechanical pieces control what's going on. If I tried that experiment again with my eyes open instead of closed, it would go even better. As my fingers get closer to each other, I can see their positions and make tiny adjustments. I use my eyes to perceive, and I control my arms and fingers with my muscles. And there's a closed loop between them. They're all part of my body and connected to my brain. It'd be a totally different problem if there was an open loop, or control without feedback. Like if I close my eyes and try to touch my fingers to someone else's. My brain can't perceive with their eyes or control their muscles, so I don't get any feedback and basically have to keep doing whatever I start doing. We use closed loop control in lots of situations without even thinking about it. If a box we're picking up is heavier than expected, we feel it pull the skin on our fingers, so we tighten our grip. And if it's even heavier than expected, we might use our other hand. And if it's still too heavy, well, we'll call over our open loop example buddy. But this process has to be programmed when it comes to building robots. Manipulation can look different depending on a robot's hardware and programming. But with enough work, we can get robots to perform specific tasks, like removing the cream from an Oreo. Beyond building capable robots that work on their own, we also have to consider how robots interact and coordinate with other robots and even humans. In fact, there's a whole field of human-robot interaction that studies how to have robots work with or learn from humans. This means they have to understand our body and spoken language commands. What's so exciting about robotics is that it brings together every area of AI into one machine. And in the future, it could bring us superpowers, help with disabilities, and even make the world a little more convenient by delivering snacks.
Here you go, Jabril.
Thanks, John Greenbot. Go give me a spoon. But we're still a long way from household robots that can do all of these things. And when we're building and training robots, we're working in test spaces rather than the real world. For instance, a lot of work gets done on self-driving car AI before it even gets to an actual road. We don't want flawed systems to accidentally hurt humans. These test spaces for AI can be anything from warehouses, where robots can practice walking, to virtual mazes that can help an AI model learn to navigate. In fact, some of the common virtual test spaces are programmed for human entertainment. Games. So next week, we'll see how teaching AI to play games, even games like chess, can help us solve real-world problems. See you then.
Crash Course AI is produced in association with PBS Digital Studios. If you want to help...
So there you get that bigger feel that even AI itself and what's required from there can be more complex if you're dealing with robotics specifically. Like I said, we're not going to really have time in this course to go into that. By the time it's just going through the basics as we step forwards. But if someone's interested, then, well, maybe something can be redesigned in the course that you can individually work and go deeper into that actual realm. So in these notes here, just give you this first general introduction of, well, what is a robot? What is robotics? The different fields that are involved in robotics and study to be able to actually do this, where you can branch out and do your research, build up some terminology with the effectors, actuators, controllers, power sources. You have that robotic control loop that continuously cycling and sensing the actual environment and what's going on. And so next we'll start going into dealing with like digging deeper. So we'll be dug deeper from that sense thing act loop and get into like the effectors and actuators. Well, now we've got to get into, well, building a basic knowledge of electronics, which again is its own whole field, and you can go do multiple courses and all of this. So this is just going to be a basic starting introduction and then build off from there. So I hope that everyone is still doing good by this end of this lecture, and I would hope again that, like, even just beyond this course, that you make sure to take care of yourself, to make sure that you are doing good and that those around you are doing good. And remember that even small actions can have a big difference. Of just smiling at someone during the day and acknowledging their existence and making sure that, hey, is that person okay, or what's going on, or yourself or someone you know. Other than that, I hope that you have a great rest of your week.